Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are discussing quantum systems. So, in the last lecture, we had started the study of the ground state of the transverse field Ising model. The transverse field Ising model has a global Z2 symmetry and it has two energy scales associated with an Ising term between qubits arranged in a chain and a transverse field in the x direction in the qubit space. So, we know the ground states when the exchange constant is positive and the transverse field is 0. So, that is a ferromagnetic state, and we know the ground state when the exchange constant vanishes and the transverse field is non-zero, and there the state is x polarized state with no symmetry breaking. And the question we were exploring is how does the system evolve as you go from a small value of h compared to j to a large value of h compared to j, and we put out a set of options. It could be a crossover, it could be a first order transition, or it could be a continuous transition. So, based on our perturbative calculations near the ferromagnetic state, we were able to conclude that the broken symmetry state is stable. That means that there is a regime for small values of h by j where this ferromagnetic phase with broken symmetry survives, albeit with a smaller value of the order parameter. Even more interestingly perhaps, we found that the system is gapped, the excitation gap comes down linearly in the transverse field, and what this transverse field does is it gives dynamics to the domain wall excitations and they make them into quantum mechanical particles. Okay. By itself these results were quite exciting, and it is very natural for us to now explore the other side, namely the regime where j is much smaller than h, and we will start with the state where j is equal to 0 and little h is positive, and we will see what are the excitations and so on. So, it is a good idea to revise the notation so that you will be able to follow the lecture smoothly. So, we are discussing the chain with n sites. So, at each site we have a qubit with two-dimensional Hilbert space spanned by this eigenstate of the Zi operator at that qubit. So, this Si's can be plus or minus 1. The Hilbert space of the full system is the tensor of the Hilbert space at each of these sites, and the dimension of the Hilbert space is 2 to the n. So, the Hamiltonian has two pieces. There is this transverse field piece, this is the transverse field piece, and there is the Ising piece here, and the Ising piece has a coupling constant j and the transverse field has coupling constant h. The global Z2 symmetry is generated by this product of x operators, and the goal of our study is to investigate the regime where h by j is much greater than 1, or if I put it the other way around, j by h is small. So, the ground state for j is equal to 0 and h greater than 0 is the right polarized state, which are just the eigenstates of xi operators, and you just tensor product those guys. That will be the right polarized state, the fully right polarized state. And by the very construction of this state, this order parameter m, which is the expectation value of 1 by number of sites sum over the Zi operators, expectation value of that state, that will be 0. So, it is pretty clear that this state will not break the Z2 symmetry. In fact, the state is an eigenstate of the flip operator with eigenvalue plus 1. So, what we are now going to do is we are going to set up a perturbation theory keeping j by h as a small parameter. So for that, I need to know the spectrum, the low-lying excited states of the system when J is equal to 0. This is the ground state. I need to know what is the spectrum above that. So the spectrum at, sorry, this is a typo. This should be J is equal to 0, not H is equal to 0. Okay, this thing should be J equal to 0. So for J is equal to 0 and H greater than 0, this problem reduces to a set of decoupled qubits, and that has this unique ground state with ground state energy minus n times H. So that state is pictorially represented in this fashion. So I have all the qubits to be X polarized. It's a schematic picture. Please don't think that the X of the qubit is same as the X axis of space. X is in the qubit is some direction in the qubit space. So we are just schematically showing it to be in the X axis of our system. Okay, what are the first excited state? So what I could do is I could go to a particular site and I could flip the spin to negative X, that is its point, the spin is polarized in the other direction. That is what we mean by this. So this state will be 2H above the ground state of this qubit, and therefore this state will be 2H above the ground state. Okay, and it will also have a degeneracy of n. What do I mean by degeneracy of n? This I left can be located anywhere on the chain. All of those states have equal energy, and hence the degeneracy of n. Okay, what is the next excited state? So you will see that this state is not of immediate importance to us. This will take, we will see that in the next coming slides. The next excited state has two X flipped sites. So what do we mean by two sites? So there is, so you can choose I1, you can choose a convention where I1 is less than I2. So what you will have is, you will have a spin flip to the negative X polarized state here, and spin at I2 is also negative X polarized. So this state will be 4H above the ground state. So it is twice as higher in energy as the single spin flipped system. This manifold of the states at 4H energy are also more degenerate, and their degeneracy goes as n times n minus 1 by 2. So it turns out that this manifold, not the first X, not this one, this manifold is what will be important for us. Okay, and that, mind you, comes from the Ising symmetry, as we will see. Okay, we can list out all the excited states just like we did. We can list out all the excited states for the system in the ferromagnetic state. You can excite any number of such single spin flip to negative X polarization. So I am just showing you a picture here with 4 such states, and you will see that if you work this out, the leading power in n of degeneracy will go as n to the power 4. So you can see that this will get interesting. Of course, if you flip as many numbers spins as the order of the system size, then it will actually, the number of states will start coming down. So you can work, it's an interesting question, you can work it out yourself as to what is the degeneracy for arbitrary number of spin flips. Okay, so we now have an idea of what is the ground state and the spectrum. Okay, now let's explore what is the ground state at a J which is much smaller than H. For the ferromagnetic case, the calculation is very straightforward. Here you will realize we have to prepare for the calculation a little bit more carefully. Okay. So, to perform the perturbative calculation, I have to look at the operators that produce the excitations. Those are the Ising terms. Now, those Ising terms are written in the, and we are usually writing all these matrices in the Z polarized basis. That is the basis we chose. So, now these Ising terms, to make them natural, we have to write the Ising term in a manner that allows us to look at the creation and destruction of excitations. So, for this I take the Zi operator, which remember is just diagonal 1 minus 1, and I split it up into two operators which I call sigma plus at site I and sigma minus at site I. So, what is sigma plus at site I? That I am simply defining it. It is 1 half 1 minus 1 1 minus 1, and this is sigma minus I 1 half 1 minus 1 1 minus 1, so or 1 1 minus 1 minus 1. So, you might wonder, like, this is a rant of some middle-aged guy sitting and playing some games with matrices. You add them, of course you get Z. So, what is the big deal, you may wonder. The big deal is the following. These operators act as the rising and lowering operators of the X polarized state. So, for example, if I hit sigma plus on the right polarized state at I site, I will destroy that state. On the other hand, if I hit sigma plus on the left polarized state, I will lift it up to the right polarized state. Sigma minus does exactly the opposite. It will take the right polarized state and shift it to the left polarized state, but if you send it the left polarized state, it will kill it. So, this is exactly what your S plus S minus operators that you have studied in angular momentum or spin angular momentum quantum mechanics are doing, but now written in the basis that makes natural to study the X polarized state. Or so this is the natural form of the matrices that will be useful to study our problem, because we have posed the problem in the Z polarized basis states. So, we have to write the sigma plus sigma minus terms that will flip the X polarized state, and that is why they look funny in this fashion. Very good. So, where do I go with this? Okay, now observe that if I take Zi plus 1 and Zi, I can split this term with this object at I plus 1 and same thing here at I, and I can expand that product. So, I will end up getting 4 terms which I make into 3 groups. So, this term are both plus from I plus 1 as well as I. This is a term which is minus for both the sides involved, I plus 1 and I. Here I have yet another term where I group 2 of these. So, this sigma plus I plus 1, sigma minus, and then sigma minus sigma plus. Okay, there is a reason for doing this, as you will see. So, now I put this whole thing back into the transverse field term, I am sorry, the Ising interaction term, and I write this and I make 3 groups again. So, the first group is what I call as H plus J, and this involves the minus minus term. So, that is what I call H minus J, and this I am going to call as H T, and you will see why it is called T later. Okay, this term. Okay, so this is how far I have got with this manipulation, which I am going to use to perform my perturbative calculation. Okay, let us compute the ground state energy for small j. So, the first observation you want to do is that when Hj hits on the right polarized state, it produces states with 2 sites with X spins flipped. The reason for that is Z operators will involve sigma minus operators which will produce the spin flips. So you see this by the action of this operator sigma minus I plus 1, sigma minus I plus 1 acting on the right polarized state. That will give you a state which is one negative X polarized state at I and another negative X polarized state at I plus 1. So that is in our notation a ket written like this. These are the states I can reach at first order in perturbation theory when I hit my perturbation which is Hj on my right polarized state. These are the states I can reach. And how many such states can I reach? I can reach n such states where there are n such operator sigma I plus 1, sigma minus I plus 1 and sigma minus I. There are n such operators where on each nearest sites I perform the sigma minus operation. Okay. So what do I have to do to compute the ground state energy? So to compute the ground state energy, I just use the same result, and remember the linear order term vanishes here as well, because if I hit HH on the right polarized state, I will produce 2 spin flips which is orthogonal to the state which is right polarized, and therefore there is no linear term. So to get the quadratic term, I just go to the excited state manifold and come back to the ground state manifold. That's a way to think about this. And for this, I take the matrix element between the right polarized state and the H minus, because all other things will not, none of the other terms will contribute, H plus or HT will not contribute, and it will give me a matrix element with these states. And there are n such states, please remember. So you will see that this matrix element is simply J, and if I square it, I will just get J square, and I will get a factor of n because there are n such terms here. So if I work out the details now very straightforwardly, I will see that the ground state energy is minus nh times 1 plus 1 by 4 little j by h whole square. Yes, we did a little bit of work, not very difficult, but we are very pleased that this is correctly extensor. Okay, good. So what about the order parameter? So if I now turn on a little bit of j, remember when j is 0, the order parameter is exactly 0. Does it produce some order parameter? Let's work this out. So if you look at the unnormalized ground state, you will see by the same simple elementary arguments, the ground state at any j which is non-zero is the right polarized state plus the matrix element to the excited state divided by the energy denominator, which is minus 4h, and this is the matrix element. The matrix element is just minus j times the excited state. Okay. So the ground state now has the right polarized state admixed with a set of nearest neighbor negatively x flipped states admixed in this, quantum mechanically admixed into this. Okay. Now you can easily compute the magnetization using the operator, and you will instantly see that the magnetization is 0. Why do we see that it is 0? Because you see this is right polarized state, so that will contribute nothing to this. If I hit M on this state, you see they are still, every qubit is an eigenstate of the x. In some states here, for example at I and I plus 1, they are in the eigenstate of the x operator of the qubit. Therefore, the expectation value of the z operator on those will be 0. And for that very simple reason, you will see that this quantity is 0, and therefore the whole magnetization itself is 0, and magnetization is 0 for a small j. So this causes for us to be a little bit excited now. So what we are finding is that the Z2 symmetric state survives even for a small finite j, it survives. So, I have no order parameter even when j is non-zero, but much smaller than h. Okay, so the Z2 symmetric state survives, and the small reward for us for the work we have done now is that we have eliminated the possibility of the crossover. So, why is that the case? So, if I had a crossover, then when h by j is very large, in other words j by h is very small, then I would have had some small magnetization. But my perturbative calculation has established that such a magnetization will not arise, and therefore we can safely ignore this possibility of crossover, and we have come to the conclusion that there are only two possibilities, one of a continuous transition and the other of a first order transition. Maybe you would like to guess which one is the one? Okay. So, it is not enough to simply guess, you should try to make a logical guess, you have to have some physics reasoning for that guess. So, please do think about this. So, I am going to proceed with the lecture. So, we have already with our calculations made some progress in understanding the phase diagram at 0 temperature, or the, let us say, the what are the possibilities of how the ground state will evolve. It is also natural to inquire about the excited states when I have h is equal to 0 and a small j, h is greater than 0 and a small j. So, remember that the excitation gap of all the accessible state, will make clear what accessible means, is 4h when j is equal to 0, right. Now, important thing to note is that if h plus j acts on any of these excited states, they will produce more excitations. So, h plus will actually reduce the number of negatively polarized x states, and h minus will increase the number of negatively polarized x states. Okay. So, this is what happens, and it will take the states out of the 4h excited manifold. So, these operators are not immediately of interest to us because they are taking us out of the first excited manifold, which is at 4h. So, what are the which operator now keeps us in the same manifold of energy 4h, but produces some admixing in the states associated with that 4h energy manifold. So, my claim is that this is the HT operator. So, remember, the HT operator is a linear combination of sigma plus, sigma minus on neighboring sides. Okay. So, what I am going to do is, I am going to call a state called Li. So, what is the state Li? Li has a negatively expolarized state at 0 that we are fixing, and there is a negatively polarized x state at site I. So, this definitely is in the 4h energy manifold. Now, I ask, what does this operator do here? So, you see what it does is it does sigma plus here. So, when I do sigma plus, this spin will flip back and it will straighten out to it will come to the plus x, and when the sigma minus I plus 1 acts, it flips this spin to the left. So, what have I done? I hop this negative spin flip by one side. So, this term produces a hopping of this negative spin flip. So, this is looking very intriguing. So, what I am just demonstrated to you is that the action of this operator on Li will produce Li plus 1. Okay. So, we can use the very same ideas that we did work out when we looked at the ferromagnetic system. and did perturbation about the ferromagnetic state. And you can compute the matrix element of these states, where I am computing the matrix element between Lj and Li, and it will have an energy associated with the excitation manifold of 4H, that is just coming for the ride, and that will operate only when I is equal to J. And this 4H can be thought of as energy of one of these flipped spins and the energy of the other flipped spin. So now if you keep the energy of one of these flipped spin aside and sort of think about the manifold generated by the Hamiltonian generated by this, you can make this 4H into 2H, and you can work out the tight binding Hamiltonian and its eigenstates, and you will see that you will get a dispersion E of k, which is 2H minus 2J cos k. How do we interpret this? You can again think of 2H as the energy required to create one of these downspins. That downspin meaning the negative x polarized spin. And this is the kinetic energy gained by hopping. And the hopping matrix element is this exchange constant. And what does this do? It will reduce the energy of the excitation from 2H to something. Say for example, if you put k equal to 0, you get 2H minus 2J. And J is a small positive number compared to H. So it will reduce the energy a little bit, but it will not close the gap. So what we have learnt is that the system will remain gapped when I turn on J, but the gap comes down. Okay. So even this very rough calculation, it's not an exact calculation, it's a rough calculation. You can actually go ahead and do the exact calculation. It's a little tedious, but it can be done. It shows you that you have particle-like excitations coming out of the system, even in the other side of the parameter regime, when J is small compared to H. And what I am just hoping to convince you is this is another toy universe. So if you start imagining things, you will see that the transverse yield Ising model can be thought of as some microscopic model for some universe with qubits arranged and so on. So they will see the vacuum, which is the ground state at the given J. So it is some right polarized state with an admixture of nearby negatively x polarized linear combination. And suppose they had particle colliders like we have at CERN or something like that. In that world, you can produce these excited particles, and those particles you have to pay an energy of order 2 to create a pair of particles. You have to create give an energy of 4H, and you will see that these X particles, if there is a dilute version of them, you will see them dispersing with this kind of a dispersion relationship. Okay. Now quite remarkably, even here these particles can only be created in pairs. Using our Hamiltonian, you will only be able to create in pairs because you have to have symmetry preserved. Remember, ZZ term is what makes it the product of two Z's, and therefore you will excite only by pairs. And in this sense, they are their own antiparticles as well, because you create them in pairs and you can also destroy them. So you can sort of imagine that when I take this particular state and do sigma plus on them, I flip both of them back. So you can sort of think that these particles are destroying each other, and that's the way to think about this. So the fact that I am able to create this in pairs is actually a consequence of Z2 symmetry. So remember that I had told you of the excited states, there was one of them with a single spin flip. Sorry, I'll show you the picture a little. I had a single spin flip state. You see, this never appears in my discussion if I have Z2 symmetry. But if I break the Z2 symmetry by hand, then I can actually create this particular state. Why is that? Because I can add a term in the Hamiltonian which is just proportional to Z, Zi here. and that is sigma plus sigma minus, so it can actually produce a single excitation at the site, but now you see the problem does not have Z2 symmetry. Okay. So Z2 symmetry is what forces these particles to be created in pairs and so on. Okay, so that's very interesting, but I want to bring in some more intrigue into the discussion. So we have solved the problem in two limits, in the ferromagnetic limit and in the symmetric limit. So in the ferromagnetic limit, J was positive and H was nearly 0, and in the other limit, H was positive and J was nearly 0 compared to H. So let's just collect all these results in a table. Okay, so that's the table. So now this is the regime where H is much smaller than J, and the energy per ground state looks like this. Okay, energy per site in the ground state looks like this. For the paramagnetic side, or the side which doesn't break symmetry, I have this expression. If I look at the magnetization, there is a non-zero magnetization here, but there is zero magnetization here. So this is somewhat different. But if I look at the excitations, I have excitations which have, you need to pay 2J energy to create them, and then they will disperse and gain some energy, and the hopping energy there is H, and here exactly the roles are reversed. So if you look at all terms associated with energy and stuff, so it looks like these results were simply exactly same as the results in the other side, with the role of H and J interchanged. So you may wonder what happened here. Did someone copy and they didn't copy things correctly? It's cut and paste and something was not copied correctly. But no, you are sure that this is not the case, because I did the calculations in front of you. So these are correct results. But is it an accident that the results are exactly same with the roles of H and J reversed, or is it something deeper? So maybe you should stop and think about this. Is it something deeper, or it's just what it is? Okay. With that point, I'm going to conclude this lecture. So let me summarize. So the perturbative analysis results gave us that for H much smaller than J, we have a broken symmetry state with order parameter non-zero, but falling with increasing H. For J much less than H, I have a Z2 symmetric state. So this discussion that we worked out with this perturbative calculation has immediately ruled out the possibility of crossover. However, it has not allowed us to answer the question whether the transition is going to be first order or continuous. We don't know the answer to this question to the level of perturbation theory we have performed. So more importantly, in my perspective at least, is that you can view this transverse field Ising model as some model of some universe where you have excitations which starts moving, etc., and these are coming from quantum fluctuations. Remember what quantum fluctuations mean? I have two operators that are not commuting. So when I take the ground state of one of the operators, let's say if you look at the ferromagnetic side, I take the ground state of the ferromagnetic Ising term, and when I operate the transverse field term, it will start to disturb that state. It will produce fluctuations in that state, and those are quantum fluctuations because of the non-commutativity of these two terms. And these quantum fluctuations is what is producing all these interesting results. But even more strikingly, what we found was that the results on these two, in this regime and in those regime, had exactly the same structure in terms of the main energy scale, which is either H or J, or the perturbative piece, which is the ratio of the coupling constant, and everything looks the same except their roles get interchanged. Now this is really intriguing, and the next lecture I'll try to resolve this intrigue, and maybe you should make an attempt to resolve it yourself before you listen to the lecture, and I will try to answer the question whether it is going to be first order or continuous. So I'm quite sure that you will be very keen to know what is the answer to this, what is the story behind these things, and I'm sure I'll see you in the next lecture. Thank you and have a good day.